Hello, you tired little peeps. It's that time once again. So let's snuggle up fast, because tonight we're traveling back in time to follow the gentle, unyielding path of water, examining the minute structural specifications and the complex distribution grids of the Roman aqueduct systems. So if you are new to the channel or returning, liking the video significantly helps. Also, please let me know where you're listening in from and what time it is for you. Now get comfortable and let's begin. Before we can witness the grand arches stretching across the valleys of the Campania, or hear the rush of water filling the great baths of Caracalla, we must first stand in the silence of the untouched hills. We must begin where the water begins, long before the first stone is quarried, long before the mortar is mixed. We begin with the concept of the source and the meticulous, almost tedious planning required to move a heavy, fluid element from the high mountains to the bustling city center, using nothing but the constant, reliable force of gravity. The story of the Roman aqueduct is not merely a story of architecture, it is a story of extreme precision. It is a narrative written in millimeters of slope and degrees of decline. To understand the structural specifications, we must first understand the raw materials and the geography that dictated them. The Romans did not simply find water and pipe it. They curated it. They analyzed it. They categorized it based on taste, temperature, clarity, and the health of the animals that drank from it. Imagine standing on a hillside in the Apennines. It is quiet here. The wind rustles through the dry grass. A Roman surveyor, a librator, stands beside a bubbling spring. He is not looking at the view. He is looking at the ground. He is looking for signs. Vitruvius, the great architect whose writings guide much of our understanding of these processes, described the tests for finding water with an almost obsessive attention to detail. Before a route could be planned, the quality of the water had to be assured. They would look at the complexion of the people living near the source. Were they healthy? Were their eyes clear? If the locals were strong, the water was deemed worthy of Rome. They would sprinkle water on a bronze vessel and wait to see if it left spots. They would boil it in a copper cauldron and let it stand, checking for sediment of sand or mud. This preliminary phase, often lasting months, was the quiet foundation of the entire system. Once the source was approved, the true work of the laboratories began. This is where the structural specifications find their origin, in the measurement of the land. To transport water over distances of 40, 50, or even 90 kilometers, the gradient had to be perfect. If the slope was too steep, the water would rush with destructive force, eroding the bottom of the channel and damaging the structure. If the slope was too shallow, the water would stagnate, allowing algae to grow and sediment to settle, clogging the artery. The ideal, the golden ratio of the aqueduct, was a slope of roughly 1.5 to 3 meters per kilometer. Just think about that for a moment. Over a distance of 1,000 meters, the elevation change might be as little as the height of a person. Achieving this over rugged, uneven terrain required tools of surprising complexity and surveyors of immense patience. The primary tool used for this task was the chorobates. Let us visualize this instrument, for it is the grandfather of the modern spirit level. It was not a small handheld device. It was a massive wooden bench, roughly 6 meters or 20 feet in length. It was built from seasoned wood, likely oak or pine, chosen for its resistance to warping under the sun or swelling in the damp morning air. The wood would be sanded smooth, heavy, and solid. At each end of this 20-foot beam were legs, carved to be perfectly perpendicular to the top surface. But the ground is rarely flat, so the chorobates had to be adjustable. Diagonal braces connected the legs to the main beam, ensuring rigidity. From the sides of the beam, weighted strings, plumb lines, hung down. These were the simple, undeniable judges of gravity. When the lines struck specific marks carved into the braces, the surveyor knew the table was level. But the Romans knew that wind could disturb a plumb line. A slight breeze in a valley could sway the string just a millimeter, throwing off the calculation for miles. So, carved into the very top of the 6-meter beam was a groove. A long, shallow channel, 5 feet long, perhaps an inch deep and an inch wide. Into this groove, the surveyor would pour water. If the water filled the groove evenly, touching the rim at all points without spilling over one side, the instrument was perfectly level. This method, using the surface tension and self-leveling nature of water itself to measure the path for future water, was the standard of the day. Imagine the process of using this tool. It is slow. It is repetitive. The survey team places the chorobates on the ground. They check the plumb lines. They adjust the wedges under the legs. They pour the water into the groove. They wait for the ripples to settle. They sight along the top of the beam to a target rod held by an assistant 100 feet away. They record the elevation. Then, they pick up the heavy wooden bench, walk forward to where the assistant stood, and repeat the entire process, again, and again, and again, for 50 kilometers, through forests, over rocks, across marshes. This is the monotonous rhythm of engineering. In addition to the chorobates, they use the dioptra for more complex angles, and the groma for creating straight lines and right angles. The groma consisted of a vertical staff with a cross piece mounted on a bracket that could turn. From the 4 ends of the cross piece hung 4 plumb lines. By sighting along these lines, the surveyor could stake out perfect squares and straight avenues. The precision of the groma allowed the aqueduct to navigate the landscape in straight, efficient segments, turning only when the topography demanded it. Once the route was mapped and the gradient calculated, the structural specifications for the channel itself, the specus, came into play. Contrary to the popular image of aqueducts as high stone bridges, the vast majority of the Roman water system was underground. In fact, of the roughly 500 kilometers of aqueducts serving the city of Rome, only about 50 to 60 kilometers were above ground on arches. The rest, over 85%, lay buried beneath the earth. Being underground offered protection. It protected the water from the heat of the sun, which would encourage bacterial growth. It protected the water from freezing in the winter, and perhaps most practically, it protected the water from enemies who might seek to cut the supply. The standard specification for a subterranean channel involved a trench, dug deep into the soil or hewn from the living rock. Let's focus on the dimensions. The channel was usually rectangular in cross-section. It was large enough to allow a man to walk through it for maintenance, typically about 1 meter wide and 2 meters high. This human-scale dimension was a crucial structural spec. It meant that every meter of the aqueduct, from the source to the city, was accessible by a worker with a lamp and a shovel. The floor of the channel, the solum, was the most critical surface. It was constructed of concrete, but not just any concrete. The Romans used a specialized mix known as opus signinum. This material was a blend of lime, sand, and crushed pottery or tiles, broken bricks, roof tiles, amphorae fragments. The crushed ceramics gave the mortar a reddish or pinkish hue, but more importantly, they gave it hydraulic properties. It was waterproof. The preparation of opus signinum was a labor-intensive process. The lime had to be slaked, mixed with water, and left to mature. The sand had to be sharp and free of earth. River sand was preferred over sea sand, which contained salt that could weaken the bond. The pottery shards had to be pounded to a specific aggregate size, not too dusty, not too chunky. When mixed together and rammed onto the floor of the trench, this material cured into a surface that was hard as rock and impermeable to water. The walls of the channel were often built of stone masonry or concrete faced with brick, also lined with opus signinum. But they did not just line the walls flat. At the junction where the wall met the floor, the Romans often installed a quarter-round molding. This was a curved fillet of mortar that eliminated the sharp 90-degree angle at the bottom corners. Why? Because sharp corners trap sediment. Sharp corners are harder to clean. A curved corner allows the water to flow more smoothly and makes the job of the maintenance worker sweeping out the mud much easier. It is a tiny structural detail, unseen by the public, but it speaks volumes about the foresight involved in the design. The roof of the underground channel varied depending on the depth and the available materials. In loose soil, a vaulted roof made of concrete or stone voussoir was common, providing the strength to hold back the earth above. In rockier terrain, flat stone slabs might be used to cap the channel. The interior was dark, cool, and damp. The only light came from the inspection shafts, or puttae. These vertical shafts were dug at regular intervals, typically every 70 to 80 meters, or every 240 Roman feet. They served multiple purposes. During construction, they allowed workers to remove the excavated soil without hauling it all the way to the end of the tunnel. They provided ventilation for the workers and for the curing concrete. Once the aqueduct was operational, they acted as service entrances. Imagine the view from inside the channel, looking up a long, dark shaft to a small circle of daylight far above. These shafts were marked on the surface, often with a stone kippus, a marker post, warning farmers not to plow too close and damage the access point. Now consider the sheer volume of material required for just 1 mile of this underground conduit. Thousands of tons of rock excavated, thousands of tons of sand and lime imported, the timber required for shoring up the trenches, the water needed just to mix the concrete. The logistics of the construction site were a boring, endless stream of carts and mules, oxen dragging wagons of tufa blocks, men mixing mortar in pits, the sound of pickaxes hitting the earth, rhythmic and dull, echoing from sunrise to sunset. The structural specifications changed when the aqueduct encountered an obstacle, such as a mountain or a deep valley. If a mountain stood in the way, and going around it would ruin the gradient or add too much length, the Romans tunneled. The longest aqueduct tunnel, for the Anio Novus, was over 2 kilometers long. Tunneling was the most dangerous and difficult part of the work. Without a compass, keeping a tunnel straight underground was a nightmare of geometry. They would often dig from both ends to meet in the middle. To ensure they met, they would sometimes use the kanat method, digging vertical shafts down from the surface to guide the horizontal digging. But deep under a mountain, shafts were impossible. In those cases, they relied on careful calculations of angle and distance. Sometimes they missed. There are records and archaeological evidence of tunnels where the two teams missed each other by a few meters, forcing them to dig a connecting cross-tunnel, creating a disjointed kink in the line. The sound of the other team's picks growing louder through the rock must have been the most relieving sound in the world to those miners working in the suffocating dark. When the tunnel was finished, the lining process began again. Opus signinum on the floor, waterproof cement on the walls. The darkness of the tunnel was absolute, broken only by the flickering oil lamps which consumed the limited oxygen. The air quality in these deep tunnels was a constant concern, requiring the digging of ventilation shafts wherever the rock cover allowed it. But what if the obstacle was not a mountain to go through, but a valley to cross? This brings us to the most iconic structural specs of the aqueduct system: the arcades, the bridges, and the siphons. While the underground channels were the workhorses, the bridges were the showpieces, though their primary function was purely utilitarian, to maintain that precious, steady gradient. A simple low wall, a substructure, might suffice for a shallow depression, but for a deep valley, the channel had to be elevated. We are talking about building a stone river in the sky. The foundation of an aqueduct bridge had to be incredibly robust. The Romans would dig down to the bedrock to seat the piers. If the ground was swampy or unstable, they would drive piles, wooden stakes tipped with iron, deep into the mud until they hit solid ground, creating a friction pile foundation. On top of these piles, they would pour concrete. The piers themselves were built of massive stone blocks, often laid without mortar, held together by iron clamps set in lead. This dry stone masonry allowed for a certain amount of shifting and settling without cracking the structure. The stone used was typically local, travertine, tufa, or limestone. The surface of the stone was often left rough or rusticated, which not only saved the effort of smoothing it, but gave the structure a sense of weight and connection to the earth. The arches that spanned between the piers were semicircular. This is the hallmark of Roman architecture. The structural spec for the arch relies on the voussoir, the wedge-shaped stones that form the curve. The weight of the structure pushes down on the keystone at the top, which distributes the force outwards and downwards through the voussoir and into the piers. It is a system of compression. Stone is incredibly strong in compression, meaning it can support a lot of weight pushing down on it, but it is weak in tension, being pulled apart. The arch converts the weight of the water channel above into purely compressive forces. However, there is a limit to how high a single set of arches can go before the piers become too tall and unstable, liable to buckle. The Roman structural solution to this was the tiered arcade. If the height required was more than about 21 meters, they would build a second row of arches on top of the first. The Pont du Gard in France is the supreme example of this, with 3 tiers of arches reaching a height of nearly 50 meters. The specifications for these tiers were rigid. The piers of the upper tier had to sit directly on top of the piers of the lower tier to create a continuous line of vertical support. The arches on the lower tiers were wider and thicker, while the arches on the very top, carrying the actual water channel, were smaller and more numerous. This distribution of mass kept the center of gravity low and the structure stable against the wind. When the valley was too deep for even a 3-tiered arcade, or when the cost of stone masonry became prohibitive, the Roman engineers turned to a different, more daring structural specification: the inverted siphon. This mechanism relied not on the gentle flow of an open channel, but on the principles of pressurized hydraulics. It was a closed system, a test of material strength that pushed the limits of ancient technology. The concept is simple in theory, based on the principle of communicating vessels. Water dropped down one side of a valley in a closed pipe would rise up the other side to nearly the same level, driven by its own weight. But the execution required specs of extreme rigor. An open stone channel could not withstand the bursting pressure of the water at the bottom of a deep valley. The masonry would simply crack and leak. Therefore, the water had to be confined within materials that offered tensile strength. Lead, or more rarely, bored stone or ceramic encased in concrete. The structure of a siphon began with a header tank or a receiving basin situated at the edge of the valley. Here, the open water of the masonry aqueduct flowed into a reservoir. The water slowed, swirled, and then entered a series of parallel lead pipes known as fistulae. Why parallel pipes? Because a single pipe large enough to carry the entire flow of the aqueduct would be too difficult to manufacture and too weak to withstand the pressure. A battery of 8 or 10 smaller pipes was safer and easier to repair. If one burst, it could be isolated while the others continued to function. These lead pipes descended the slope of the valley, supported on a ramp of earth or stone. At the bottom of the valley, they did not just lie on the ground. They crossed a low bridge known as the venter or the belly. This bridge served a crucial structural purpose. It reduced the maximum depth of the siphon, thereby reducing the maximum pressure the pipes had to endure. From the venter, the pipes ascended the opposite slope, entering a receiving tank slightly lower than the header tank, a loss of height known as the hydraulic gradient, necessary to overcome friction within the pipes. The specifications for these lead pipes were standardized with bureaucratic precision. We know from Sextus Julius Frontinus, the curator aquarum or water commissioner of Rome in the late 1st century AD, that the pipes were categorized by their diameter. The most common unit was the quinaria, a pipe made from a sheet of lead 5 digits wide. The fabrication of these pipes was a monotonous industrial process. Lead was mined, often in Britain or Spain, and transported in heavy ingots, or pigs, to the construction site or a central foundry. The lead was melted and cast into flat sheets of uniform thickness, typically around 1 centimeter thick. The sheet was then wrapped around a wooden core or dowel to form a tube. The edges of the sheet were not merely overlapped. They were pinched together to stand up in a ridge and then soldered with a mixture of lead and tin. This created a pear-shaped cross-section rather than a perfect circle. The soldered ridge was the weak point, the seam that had to hold against the crushing weight of the water column. Every length of pipe, usually about 3 meters long, was heavy and inert. Joining them required pouring molten lead around the joint, fusing the sections into a continuous snake of metal. The sheer amount of lead required for a large siphon is staggering. For the siphon at Lyon, in Gaul, it is estimated that thousands of tons of lead were used. This was a display of imperial resourcefulness, the ability to move mountains of metal to move rivers of water. The pipes were also stamped. In the wet concrete or on the soft lead, we often find inscriptions. These stamps are the paperwork of the construction. They list the name of the emperor, the name of the manufacturer, the name of the plumbing contractor, and the capacity of the pipe. It was a system of quality control and accountability. If a pipe burst, the stamp revealed who was responsible. As the water left the siphon and returned to the masonry channel, it resumed its gentle, gravity-fed journey. But as the aqueduct approached the city, the water required purification. While the source selection was the first line of defense, the journey itself introduced impurities. Leaves, dirt, and accidental debris could enter the channel through inspection shafts or damaged covers. To address this, the structural specifications included settling tanks, known as piscina limaria. A piscina limaria was essentially a disruption in the flow. It was a large, vaulted chamber lined with the same waterproof opus signinum. The floor of this chamber was set lower than the floor of the aqueduct channel. As the water entered this expanded space, its velocity decreased significantly. Physics dictated the result. When the speed of the water drops, its ability to carry suspended particles diminishes. The sand, mud, and heavier pebbles would slowly drift down to the bottom of the basin, settling into a thick layer of sludge. The cleaner water would then flow out over a weir or lip at the far end of the chamber, continuing towards the city. These tanks were equipped with a drain in the floor, controlled by a sluice gate. Periodically, the flow would be diverted, or the tank would be isolated, and a maintenance crew would descend into the damp, echoing chamber. They would open the drain and shovel the accumulated muck out into a nearby stream or onto the fields. It was a dirty, repetitive job, essential for keeping the water clear. Some aqueducts had multiple settling tanks along their route, ensuring that by the time the water reached the urban distribution center, it was as transparent as glass. Now, let us follow the aqueduct as it finally reaches the city boundary. The structure changes again. It is no longer just a conduit. It becomes a monument. As the arches march towards the city walls, they often become taller and more ornate. They pass over roads and through gates. The Porta Maggiore in Rome is a prime example, a massive double archway formed by the supports of the Aqua Claudia and the Anio Novus aqueducts stacked on top of each other. The rough, rusticated stone of the Porta Maggiore exudes a sense of raw power, a deliberate aesthetic choice to showcase the dominance of nature being tamed by engineering. Upon entering the city, the water arrived at its high point, the Castellum Aquae, or the water castle. This was the main distribution terminal, the heart of the urban grid. The Castellum was usually situated on one of the highest points of the city to maximize water pressure for the distribution network. The interior of the Castellum Aquae was a study in fluid dynamics and social hierarchy. The water poured from the main channel into a central basin. From this basin, the water was divided. Frontinus describes a system of 3 overflows or compartments, though archaeological evidence suggests many variations. The principle, however, was distribution based on priority. The lowest outlet, ensuring the most reliable supply, typically fed the public fountains. These were the lifeblood of the Roman populace. The water in the street basins was free and available to everyone for drinking, cooking, and washing. It flowed continuously, the overflow cleaning the streets and flushing the sewers. The next level of outlets might supply the public baths, the thermae. These vast complexes required enormous volumes of water, not just for the pools, but for the boilers that heated the caldarium. The highest outlets, the ones that would run dry first if the water level in the main aqueduct dropped, were reserved for private consumers. Wealthy Romans paid for the privilege of having running water piped directly into their domus. They paid a tax based on the size of the nozzle, the calyx, that connected their private pipe to the public supply. This prioritization was a brilliant structural fail-safe. In times of drought or repair, the private houses lost water first, then the baths. But the public fountains, the survival of the common people, would run as long as there was any flow at all. Inside the castellum, we would see a mesh of lead pipes leaving the tank, piercing the thick walls. Each pipe was fitted with a bronze calyx. The diameter of this bronze nozzle was the standard of measurement. A dishonest water official, a Aquarius, might try to widen the opening or angle the pipe to catch more flow than was recorded, a practice known as puncturing. To prevent this, the bronze calyx was stamped and hardened to resist expansion. The law stated that the pipe attached to the calyx had to be of the same diameter for at least 50 feet, ensuring the flow rate was regulated by friction and not just the initial opening. From the main castellum, the water was not sent directly to every faucet. Instead, it was routed to secondary towers, smaller reservoirs scattered throughout the distinct neighborhoods of the city. These secondary towers acted as pressure reducers. If the water fell from the main castellum directly to the bottom of a valley in the city, the pressure would burst the lead pipes and bronze taps. By stepping the water down through a series of local tanks, the pressure was kept manageable. The distribution network under the streets of Rome was a labyrinth. Thousands of lead pipes ran alongside the sewers, under the pavement stones. They branched and turned, connected by soldered joints and bronze junction boxes. The maintenance of this subterranean web was the responsibility of the Familia Publica, a state-owned gang of slaves, and later the Familia Caesaris, the emperor's own workforce. They were the ones who dug up the cobblestones to find a leak, who replaced the stolen pipes, who turned the stopcocks, bronze valves that functioned much like our modern ones, with a rotating cylinder comprised of a hole that aligned with the pipe to let water through, or turned 90 degrees to block it. The sound of the city was underscored by the sound of water, the splash of the fountains, the gurgle of the overflow, the hiss of the pressure in the pipes. But the aqueduct's job was not finished when the water reached the user. The structural specs of the system had to account for the water's exit. A city that imports 1 billion liters of water a day must also export 1 billion liters of water a day, or it will drown in a swamp of its own making. Thus, the distribution system was inextricably linked to the sewage system, the cloacae, the overflow from the fountains, the used water from the baths, and the waste from the latrines were all directed into the sewers. The famous Cloaca Maxima was the great drain that swallowed this ceaseless torrent. The constant flow of aqueduct water was essential for flushing these drains, preventing the buildup of dangerous gases and waste. The aqueduct and the sewer were two halves of the same circulatory system, one bringing clean life, the other removing toxic decay. We must also consider the materials of the distribution endpoints. The public fountains were often stone troughs, worn smooth by generations of hands resting on the rim. The spouts were often carved in the shape of animal heads, lions, wolves, dolphins, the water pouring from their mouths. These were not just decorative. The narrowing of the spout increased the velocity of the jet, making it easier to fill a jar. In the private homes, the specs became more luxurious. Lead pipes led to tanks in the attic, which fed fountains in the peristyle garden or taps in the kitchen. The taps themselves were masterpieces of bronze casting, often decorated with silver inlay. But regardless of the luxury, the water was the same. It was the same melted snow from the Apennines, carried on the same gradient, through the same dark tunnels, arriving by the sheer persistence of gravity. Let's pause to visualize the sheer scale of the maintenance required for this distribution. Calcium carbonate, or limescale, was the silent enemy of the aqueduct. The water from the mountains was rich in minerals. As it flowed, and especially as it warmed or was agitated, the minerals precipitated out of the water, forming a hard, crusty layer on the walls of the channel and the inside of the pipes. This accumulation, called sinter, could grow inches thick over years. It narrowed the channel, reducing the flow. It added weight to the bridges. It clogged the siphons. The structural specs of the aqueducts included provisions for this. The channels were oversized to allow for some buildup, but eventually it had to be removed. Workers would enter the channel with chisels and hammers. They would chip away the sinter, filling baskets with the rock-hard flakes and hauling them out through the inspection shafts. It was a never-ending cycle. As soon as they finished cleaning one section, the deposits would begin to form again. The sinter itself was sometimes used as a building material, a decorative stone, or burnt to make lime, recycling the waste of the water system. This constant interaction between the water and the stone, the eroding and the depositing meant the aqueduct was essentially a living organism, changing its internal dimensions slowly over time. The Roman engineers monitored this. They knew that a narrowed pipe meant increased pressure and reduced volume. They adjusted the flow at the intake, manipulating the sluice gates at the source to balance the system. Even the water theft, the aquarii piercing the pipes, was a form of unplanned distribution that had to be structurally countered. Frontinus writes of finding punctures in the mains, secret pipes running to illegal workshops or brothels. He describes a system of strict patrolling and heavy fines. The lead pipes themselves, buried under the pavement, were the physical evidence of these crimes. To tap into a main required digging up the street, a conspicuous act, yet it happened frequently enough to be a major administrative headache. The complexity of the distribution grid in a city like Rome cannot be overstated. We are talking about hundreds of thousands of individual delivery points. There were no water meters. You paid for the right to a pipe of a certain size, and the water flowed continuously. There were no off switches for the main supply. The surplus simply ran away. This seemingly wasteful approach was, in fact, a structural necessity. The constant flow prevented stagnation and kept the sewers functioning. The waste was a functional part of the urban sanitation specification. This constant, regulated waste brings us to the administrative structure that underpinned the physical structure. The aqueducts were not orphan monuments left to fend for themselves. They were the wards of a highly specific, rigid government department. To understand the distribution, we must understand the statio aquarum, the water office. We are fortunate to possess the personal notes of one of the most diligent managers of this office, Sextus Julius Frontinus. His writing is not poetic. It is an audit. It is a structural specification of the workforce itself. Frontinus details the composition of the maintenance crews with the same precision he applies to the width of the pipes. There were two distinct families of workers. The first, the Familia Publica, consisted of about 240 skilled slaves bequeathed to the state by Agrippa, the great builder and friend of Augustus. The second, the Familia Caesaris, was a larger body of 460 men established by the Emperor Claudius. These were not general laborers. They were specialists, their roles defined by the specific material needs of the aqueduct. There were the Vilici, the overseers who held the keys to the intake towers. There were the Castellari, the keepers of the reservoirs, men who lived in the shadow of the great distribution tanks, listening to the roar of the water day and night. There were the circuitors, the inspectors, whose sole job was to walk the line, day after day, looking for damp patches on the ground that signaled a leak, or the unauthorized growth of a tree near the channel. Then there were the craftsmen. The silicari were the pavers, responsible for the stone structures and the streets that had to be torn up to access the pipes. The tectors were the plasterers, the masters of opus signinum, the men who spent their lives inside the dark channels, troweling waterproof mortar into cracks by lamplight. The plumbari were the lead workers, carrying braziers of hot coals to melt solder for the pipes. The structural integrity of the aqueduct relied on the legal space around it as much as the stone within it. Roman law was very clear about the corridor of silence required for the system. A senatorial decree forbade any plowing, planting, or building within 15 feet of the aqueduct on either side. This 30-foot wide strip was a sacred boundary of engineering. Why 15 feet? This was the structural spec required for access. It allowed space for the carts to bring materials for repair. It prevented the roots of trees from penetrating the masonry and cracking the waterproof lining. Roots are patient destroyers. They seek water, and a tiny hairline fracture in an aqueduct is a beacon to them. Once a root enters, it grows, expanding with a force that can shatter stone. The circuitores were constantly hunting for saplings. Furthermore, the law stated that no tombs could be built near the aqueduct, and no garbage could be dumped there. The purity of the water was paramount. The penalties were steep: a fine of 10,000 sestertii for polluting the water or damaging the structure. We can imagine the sipi, the stone marker posts, standing like sentinels every 240 feet along the route, carved with these warnings, imposing a grid of order upon the wild countryside. Let us now turn our attention from the general system to the specific structural biographies of the great aqueducts themselves. Each one has a unique personality, a unique set of specifications dictated by its era and its source. The first, and the most humble in appearance, was the Aqua Appia. Built in 312 BC by the censor Appius Claudius Caecus, who also gave us the Appian Way, it set the precedent. The structural spec of the Appia was dictated by the military realities of the time. Rome was at war with the Samnites, a fierce hill people. An above-ground aqueduct would have been an easy target for sabotage. A few men with pickaxes could cut the city's water supply in an hour. Therefore, the Aqua Appia was a stealth aqueduct. It drew its water from a series of springs in the Agro Luculano, about 16 kilometers east of Rome. The water was clear and sweet. The channel was dug deep underground, tunneling through the soft volcanic tufa rock. It wound its way towards the city, staying hidden, surfacing only for a tiny stretch of fewer than 100 meters near the Porta Capena, inside the city defenses. The tunnel of the Appia was narrow, roughly 70 centimeters wide. It was a dark, cramped artery. Because it was the first, the leveling was not as confident as in later works. The gradient was somewhat steeper than necessary, dropping about 10 meters over its 16-kilometer course. It entered the city at a low elevation, which meant it could only serve the lower, flat areas of Rome, specifically the depression between the Aventine and Caelian hills. It could not climb. It was a lowland stream buried in rock. 40 years later, in 272 BC, the city had grown, and the thirst had grown with it. The spoils of the war against Pyrrhus provided the funding for the second great line, the Annio Vetus. This project introduced a new level of ambition and a new set of structural headaches. Unlike the Appia, which was spring-fed, the Annio Vetus took its water directly from the Annio River. Drawing from a river is structurally different from drawing from a spring. A spring is constant and relatively clean. A river is a living, changing beast. It rises and falls with the seasons. In the winter, it is swollen and muddy. In the summer, it flows clear but lower. The intake for the Annio Vetus was located high upstream in the Tiburtine Mountains to gain elevation. This allowed the aqueduct to deliver water to higher parts of the city than the Appia. However, the Annio Vetus was plagued by the quality of its source. Because it was river water, it was turbid. After a rainstorm in the mountains, the water turned brown/yellow with suspended soil. This necessitated a more rigorous system of settling tanks. The structural specs of the Annio Vetus channel had to account for a much higher rate of sediment accumulation. The maintenance crews spent significantly more time in the Annio Vetus shoveling mud than in the pristine Appia. Structurally, the Annio Vetus was a masterclass in contouring. To avoid building high bridges, technology and budget were still limited. The engineers made the channel follow the sides of the valleys. It hugged the hills, looping deep into every re-entrant and out around every spur. This made the route incredibly long. The distance from the source to Rome as the crow flies is perhaps 30 kilometers, but the Anio Vetus wound its way for over 63 kilometers. It was a slow, meandering serpent of stone, almost entirely underground like its predecessor. The water of the Anio Vetus was eventually deemed unfit for drinking by the elite. It was relegated to watering gardens, flushing sewers, and industrial uses like fulling, cleaning wool. It was the working-class water of Rome. Then came the Aqua Marcia. If the Appia was the pioneer and the Anio Vetus was the experiment, the Aqua Marcia was the masterpiece. Built in 144 BC by the praetor Quintus Marcius Rex, it represented a quantum leap in hydraulic engineering and financing. It was funded by the destruction of Carthage and Corinth. The wealth of the Mediterranean flowed into Rome, and Rome turned it into water. The source of the Marcia was a cluster of springs in the upper Anio Valley, known for their coldness and stunning clarity. The water was green-blue and famously refreshing. Pliny the Elder called it the gift of the gods. To bring this high-quality water to the Capitoline Hill, the symbolic heart of the city, the engineers had to maintain a high elevation. They could not afford to drop down into the valleys and lose head. This necessity birthed the long arcades. The Aqua Marcia was the first to boldly stride across the plains on miles of stone arches. The structural specs here shifted from tunneling to bridge building. The stone chosen for the Marcia was peperino and tufa, robust volcanic stones. The piers were massive. The total length of the Aqua Marcia was about 91 kilometers. Of this, about 10 kilometers were on arches. This was a visual revolution. For the first time, the aqueduct became a dominant feature of the landscape. The long line of arches marching across the Campagna became a symbol of Rome's reach. The channel of the Marcia was larger than the previous ones, allowing for a greater volume of flow. But the most significant structural specification was its elevation. It entered the city high enough to supply the tops of the hills. This changed the verticality of the city. With water available at higher elevations, wealthy Romans could build their villas on the breezy hilltops and still enjoy running fountains and baths. The aqueduct dictated the real estate market of ancient Rome. The Marcia also faced the problem of hardness. The spring water was rich in calcium. The rate of incrustation in the Marcia was notorious. Large chunks of sinter found by archaeologists in the channel of the Marcia show layers like tree rings, recording the seasons of flow. The maintenance of the Marcia required constant chipping. Following the Marcia, the demand for water continued to outpace supply. In 125 BC, the Aqua Tepula was constructed. Its name betrays its nature. Tepula, or tepid. The water was warm, around 16 to 17 degrees Celsius at the source. It was not a favorite for drinking. The structural story of the Tepula is one of piggybacking. In later years, under Agrippa, the channel of the Tepula was rerouted to run on top of the arches of the Aqua Marcia. This stacking of channels was a brilliant space-saving spec. Instead of buying a new strip of land and building a new line of arches, the engineers simply reinforced the existing Marcia arcade and built a second channel on top. Later, a third channel, the Aqua Julia, was added on top of the Tepula. Imagine the cross-section of this structure. A single line of stone arches carrying 3 separate waterproof boxes stacked like a layer cake. At the bottom, the cold, clear Marcia. In the middle, the lukewarm Tepula. At the top, the Julia. Each water source remained distinct, never mixing, traveling at different speeds, destined for different neighborhoods, yet supported by the same stones. This vertical integration is a testament to the confidence of Roman structural engineering. They trusted the foundations of the Marcia to carry triple the load they were designed for. Of course, this increased weight required reinforcement. We see evidence of later engineers, perhaps under the Emperor Titus or Caracalla, adding sleeves of brick-faced concrete around the original stone piers of the Marcia to thicken them and support the extra burden. It was a constant process of retrofitting. Let us zoom in on the construction of the channel walls themselves in these later aqueducts. We move away from the large block masonry to opus reticulatum. This was a facing technique used on the concrete core of the walls. Small pyramid-shaped stones were pressed into the wet concrete with their square bases facing out. They were set on a diagonal, creating a net-like pattern, hence reticulatum. This was not just aesthetic, it was a standardization spec. It allowed for faster construction using smaller, standardized stones that could be mass-produced by less skilled labor than the large block masons. The opus reticulatum created a strong bond with the concrete core. When you look at the ruins today, you often see this distinctive diamond pattern, a fingerprint of the late Republican and early imperial building boom. The interior of these channels was a sealed environment, but it was not lifeless. We must consider the structural spec of the ecosystem within the aqueduct. In the dark, fast-flowing water, certain things could survive. Small mollusks, freshwater snails, and sometimes even small fish would be swept from the source into the channel. We find their shells embedded in the sinter lining the walls. For the castellari at the end of the line, these creatures were a nuisance. A small fish could block a calyx. A buildup of snail shells could clog a filter. This is why the piscina limaria, settling tank, often had screens or grates, bronze meshes designed to catch this biological debris before it entered the fine distribution pipes of the city. The grid of the aqueducts also had to negotiate the existing infrastructure of the countryside, the roads. Rome was a network of roads as much as a network of water. When an aqueduct met a major road like the Via Latina or the Via Praenestina, the structural spec demanded a monumental arch. The aqueduct could not simply block the road. These crossings became architectural opportunities. The arch over the road would be built higher and wider than the standard arcade arches. It would often be decorated with an inscription stating who built or repaired the aqueduct. These are the triumphal arches of water. The interaction between the road traveler and the water traveler was vertical. The legionary marched on the stones below, while the water rushed silently in the stone box above his head, both moving towards the same destination. One of the most technically challenging structural specs was the sinter removal scuttle. In some sections of the aqueducts, specifically the ones with high mineral content, we find evidence of holes in the roof of the channel that were not full inspection shafts. They were smaller, designed perhaps for lowering tools or passing up buckets of chipped limescale. The floor of the channel also had to be treated with care regarding friction. While the opus signinum was smooth, over centuries, the water would wear grooves into it. If the floor became too rough, it created turbulence. Turbulence introduces air into the water, and it slows down the flow. Roman engineers understood that smooth flow meant efficient delivery. Periodically, they would have to replaster the floor, adding a fresh coat of waterproof mortar to restore the hydrodynamics of the conduit. This meant shutting down the aqueduct. How do you shut down a river? You cannot simply turn off the spring. The water has to go somewhere. This required diversion specs. Near the source, and at strategic points along the line, there were sluice gates that could divert the water into a nearby river or valley. When a section needed repair, the water was diverted upstream. the channel would slowly drain. The workers would enter the damp, dripping tunnel, their torches flickering in the draft. They had a limited time. The city was waiting. A dry fountain was a political problem. The pressure to repair and reopen the line was immense. They worked in shifts, day and night, scraping, mixing, plastering, waiting for the cure. And then the signal would be sent up the line to open the gates. The water would return, rushing into the dry channel, pushing a cushion of air before it. The inspection shafts would hiss as the air escaped. If the air was trapped, it could cause water hammer, a shock wave that could blow out the walls of the channel. The structural design had to ensure that the air could always vent faster than the water could arrive. This careful management of air and water pressure brings us to an aqueduct that represents a masterpiece of low-pressure, subterranean engineering, the Aqua Virgo. Commissioned by Agrippa in 19 BC, the Virgo was designed with a very specific structural purpose: to supply the new baths of Agrippa in the Campus Martius. The specs of the Virgo are fascinating because of their subtlety. The source was located in the marshy flatlands near the 8th milestone of the Via Colatina. Unlike the high mountain springs of the Marcia, these springs were barely above the level of the city. The gradient available was incredibly shallow. To make the water flow, the channel had to be constructed with an agonizingly precise slope, dropping only a few centimeters per kilometer in some sections. Because the source was low, the aqueduct had to stay low. It enters Rome from the north, tunneling under the Pincian Hill. It is almost entirely underground, which is the primary reason it has survived to this day. While the Goths and other invaders cut the high arches of the Marcia and Claudia to besiege the city, the buried channel of the Virgo remained largely untouched, invisible, and safe. It is the Aqua Virgo, renamed the Aqua Virgin, that still feeds the Trevi Fountain and the Fountain of the Four Rivers in Piazza Navona today. When you toss a coin into the Trevi, you are throwing it into water delivered by a structural system designed over 2,000 years ago, operating on the same gravity through the same restored channel. The Virgo also introduced a specific distribution spec. It was designed for public luxury. It was not primarily for drinking, though the water was potable. It was for bathing. The water was soft, meaning it had a low mineral content, which was preferred for bathing as it lathered better with the oils and soaps of the time. This shows a sophisticated understanding of water chemistry applied to infrastructure planning. In stark contrast to the purity of the Virgo was the Aqua Alsietina, built by Augustus in 2 BC. This aqueduct breaks all the rules of quality. Its water was drawn from Lake Alsietinus, now Lake Martignano, a small, stagnant volcanic lake. The water was gritty and unwholesome. Frontinus himself was baffled by it, wondering why an emperor would build an aqueduct for water that was unfit to drink. But the structural spec of the Alsietina was not for thirst, it was for spectacle. Augustus had built a massive artificial lake, a naumachia, on the right bank of the Tiber, to stage mock naval battles for the entertainment of the populace. The Alsietina was a dedicated industrial line, a single-purpose pipe designed to fill this massive basin. It is a prime example of the Roman ability to compartmentalize their infrastructure. They did not waste the sweet water of the Marcia on filling a muddy combat arena. They built a separate, lower-grade system for that. This creates a dual-tier infrastructure, potable versus non-potable, a distinction we still struggle with in modern city planning. The Alsietina had another structural quirk. It was designed to provide emergency irrigation for the orchards across the Tiber in times of severe drought, but only when the naumachia was not in use. It was a surge capacity line. As the empire moved into the era of Caligula and Claudius, the ambition of the structural specs reached its zenith. In 38 AD, Caligula began 2 new aqueducts, which were finished by Claudius in 52 AD, the Aqua Claudia and the Anio Novus. The Aqua Claudia is often considered the most impressive of all the Roman aqueducts in terms of engineering bravado. Its source was near the marshes, sharing that same high-quality water, but its structural execution was grander. The arches of the Claudia, which still stride across the Parque de los Aqueducts in Rome today, rise to nearly 30 meters. The stone blocks are massive, rusticated travertine, conveying a sense of unshakable permanence. The Anio Novus, on the other hand, was the highest of all the aqueducts. It took its water from the Anio River, but much higher upstream than the old Anio Vetus. Because of its extreme elevation, it had to travel on the highest arches. As it approached the city, the Anio Novus channel was actually placed on top of the Aqua Claudia channel. So, gaze up at those ruins again. That single line of arches carried 2 massive rivers of water, one stacked on top of the other, entering the city at the Porta Maggiore. The combined volume of the Claudia and Anio Novus effectively doubled the water supply of Rome. This was the era of the water boom. However, the Anio Novus had a flaw. Like the Vetus, it was river water. It was prone to turbidity. To solve this, the engineers under Emperor Trajan later added a massive structural improvement. They moved the intake of the Anio Novus up to a series of artificial lakes formed by dams at Subiaco, the Simbruine Lakes. These lakes acted as gigantic settling tanks. By the time the river water entered the aqueduct, the sediment had dropped out in the still waters of the lakes. This is an example of source engineering. If the source isn't good enough, you terraform the landscape to improve it. The construction of these later aqueducts brings us to a crucial material specification that made the entire system possible: Roman concrete, opus caementicium. Without this specific chemical mixture, the complex distribution, the underwater foundations, and the vast vaulted cisterns would have been impossible. The secret ingredient was pozzolana, pulvis puteolanus. This was a volcanic ash found near the town of Puteoli, modern Pozzuoli, and around Rome itself. When this ash was mixed with lime and water, a chemical reaction occurred. It didn't just dry, it reacted to form calcium aluminum silicate hydrates. This reaction is what we call hydraulic. It means the concrete could set and harden even whilst underwater. In fact, it grew stronger over time when exposed to seawater or constant moisture. This was the magic bullet for aqueduct builders. They could mix the mortar, pack it into the wooden forms for a bridge pier in the middle of a river, and the water itself would help the structure cure. The specifications for mixing this concrete were strict. Vitruvius recommends a ratio of 3 parts pozzolana to 1 part lime for underwater structures. The mixing had to be thorough. The aggregate, the chunks of rock called commenta, had to be placed by hand into the mortar, not just dumped in. This ensured that every stone was fully encased in the binding paste, eliminating air pockets. The result was a monolithic structure. A Greek stone wall is held together by gravity and friction. Remove a block, and it might fall. A Roman concrete wall is a single solid mass. It acts like an artificial rock. This is why the cores of the aqueduct arches remain standing 2,000 years later, even after the facing stones have been stripped away by thieves. The structural integrity is chemical, not just mechanical. Let's look at the distribution terminals, or castella, in more detail. Specifically, the Castellum Aquae at Pompeii, which is the best preserved example. It gives us a frozen-in-time look at the internal specs. Located at the highest point of Pompeii, near the Vesuvian Gate, this building is a small, brick-faced concrete structure. The aqueduct enters from the back. Inside, there is a circular basin. The water flows in, hits a baffle wall to dissipate its energy, and then passes through a mesh screen to catch debris. The distribution chamber features 3 pipes set at different levels, but the Pompeii spec reveals a nuanced understanding of flow dynamics. The pipes are not just holes, they are carefully calibrated exits. The internal geometry of the box is designed to reduce turbulence so that the water enters the pipe smoothly. Turbulence creates bubbles and uneven pressure, which damages lead pipes. The stillness of the water in the distribution box was a structural requirement. We also find evidence of shunting mechanisms. Simple wooden blocks or bronze slides could be dropped into slots to cut off flow to a specific sector for repairs. The system was modular. The city was divided into water zones, and the castellum was the switchboard. But what about the end of the line for the private user? The point of service specs. In a wealthy Roman domus, the water didn't just come out of a tap. It was often part of a kinetic sculpture. The pressure from the aqueduct was used to drive automata. Hero of Alexandria, a mathematician and engineer of the Roman era, describes devices where water pressure would make mechanical birds sing, or make a statue pour wine. While these were novelties, they demonstrate that the Romans understood fluid mechanics, pneumatics, and hydraulics on a sophisticated level. The stable pressure provided by the aqueduct's gravity feed was the battery that powered these devices. However, for the average citizen living in an insula, apartment block, the structural reality was different. The aqueducts generally did not service the upper floors. The pressure required to push water up to the 3rd or 4th story of a tenement building was technically possible with the siphon principle, but practically difficult due to the primitive nature of the lead pipes and soldered joints. High pressure meant leaks. Therefore, the water stopped at the ground floor. The tenants of the insulae relied on water carriers, aquarii, a term used for both the officials and the laborers, to haul water up the stairs in amphorae. The vertical distribution spec was human, not architectural. The sound of water in a Roman apartment was the sound of footsteps on the stairs, not the hiss of a pipe. Let's return to the landscape. The distribution of aqueducts across the empire followed the distribution of the legions. Where Rome went, the water followed. This was a tool of colonization. In Nîmes, France, we have the Pont du Gard. The structural spec here was determined by the river Gardon. The valley was wide and the river prone to violent floods. The bridge had to be massive. The arches of the lower tier are thick and squat to resist the lateral force of the floodwaters. The projecting stones on the face of the arches were left there intentionally to support scaffolding for future repairs, a maintenance-friendly design spec. In Segovia, Spain, the aqueduct cuts through the city center with slender, impossibly high granite arches. The spec here is dry stone. There is no mortar. The blocks are cut with such geometric perfection that they sit on top of each other, held only by balance and weight. This was a show of force. We are Rome. We can stack granite 30 meters high without glue, and it will not fall. And it hasn't. In Carthage, modern Tunisia, the Zaghouan aqueduct ran for over 130 kilometers. The structural challenge here was the heat. Evaporation was a major loss factor. The channel was covered with heavy stone slabs and buried wherever possible to keep the water cool. The inspection shafts were sealed tight. The engineering adapted to the climate. In Caesarea, in Judea, the aqueduct ran along the beach. The structural enemy here was salt spray and sand erosion. The sandstone used for the arches was plastered heavily to protect it from the corrosive sea air. We see constant layers of repair, fighting the elements. This adaptability of the structural specs is what allowed the system to scale. Whether in the freezing winters of Germany or the burning sands of Africa, the core principles remained: a consistent gradient, a waterproof channel, and a gravity-driven flow. Let's discuss the water theft prevention specs in more detail. We mentioned the stamped pipes, but there were other methods. The calyx, nozzle, inserted into the distribution tank was made of bronze, not lead. Why? Because lead is soft. A user could take a knife and widen a lead pipe to steal more water. Bronze is hard. You cannot widen it without removing it or drilling it, which is loud and obvious. Furthermore, the calyx had to be placed horizontally. If it was placed lower in the tank, the pressure would be higher and the flow greater. If placed higher, the flow was less. The law specified the exact level for each type of license. The water inspectors carried calibrated rods to measure the depth and diameter of these nozzles. It was a bureaucracy of millimeters. The overflow water had its own specs. It wasn't just dumped. It was often leased to fullers, wool cleaners, who needed urine-rich water for ammonia, collected from public urinals, and flowing water for rinsing. The overflow from the baths was directed to latrines. The multi-use cycle of water was a key efficiency spec. The water worked 3 or 4 times before it finally left the city in the sewer. Drinking, bathing, latrine, flushing, river. Or drinking, fountain overflow, street cleaning, sewer. This cascade of use required careful elevation planning. The baths had to be slightly higher than the latrines. The fountains had to be positioned so their runoff would naturally flow into the gutters. The grading of the city streets themselves was part of the aqueduct system. The camber of the road guided the wastewater to the drains. We should also mention the siphon terminals. At the end of a high-pressure siphon, like the one at Lyon, the water exits the pipe with significant force. The receiving tank had to be reinforced to withstand this kinetic impact. Often, the water was directed against a stone block to absorb the energy before it flowed into the gentle open channel again. This transition from high energy to low energy was a critical stress point. In the case of the massive Castellum Aquae of the Aqua Giulia, the Trofeo di Mario ruin in Rome, we see a multi-story distribution fountain. The structure itself was a water display. The specs here included niches for statues and a facade that looked like a theatrical stage. The water didn't just arrive, it performed. This marks the transition of the aqueduct from a purely utilitarian pipe to a piece of urban propaganda. The bricks used in these later structures are also a source of data. Roman bricks were stamped with the name of the consul and the brickyard owner. This allows us to date the construction of an aqueduct repair to the exact year. It is a metadata spec embedded in the ceramic. When we look at a wall of the Aqua Nero, a branch of the Claudia, we can read the history of its production in the clay. We must now turn our gaze to the invisible architecture of the aqueduct, the mathematics of the flow. While the arches and tunnels are the physical shell, the true structural specification is the behavior of the water itself. The Roman engineers did not possess the modern equations of fluid dynamics. They did not have Bernoulli's principle or the Manning formula for open channel flow. Yet, they achieved a consistent, reliable discharge. How? Through a rigid adherence to standardized dimensions and empirical observation. The unit of measurement that governed this entire hydraulic world was the quinaria. Frontinus dedicates a significant portion of his writing to defining this unit. It was not a measure of volume per se, like a liter or a gallon. It was a measure of capacity based on the diameter of the pipe. Specifically, a quinaria was the capacity of a pipe made from a sheet of lead 5 digits wide. When formed into a tube, this created a diameter of approximately 2.3 centimeters. However, the Romans understood that the diameter alone did not determine the flow. The head or water pressure mattered. A quinaria pipe placed at the bottom of a deep tank would flow faster than one placed near the surface. To standardize this, the structural spec required the calyx, the bronze nozzle, to be placed under a specific head of water to ensure a standard delivery. This attempt to create a universal standard for a fluid element is a testament to the Roman desire to impose order on nature. They categorized pipes into a complete sizing chart. There was the senaria, 6 digits, the septenaria, 7 digits, all the way up to the massive vicenaria, 20 digits. Each size had a specific legal area of cross-section. For example, the quinaria had an area of roughly 4.2 square centimeters. The officials calculated the total water supply of Rome not in liters per day, but in quinariae. Frontinus estimated the total intake of the 9 aqueducts functioning in his time at roughly 24,000 quinariae. But here lies the lost water structural problem. Frontinus found that the amount of water recorded at the intake did not match the amount of water recorded at the distribution tanks. There was a discrepancy of thousands of quinariae. Where did it go? Some was lost to leaks, structural failures in the masonry. Some was lost to theft. But much of it was lost to the imprecision of the math itself. The Romans assumed that if you doubled the cross-section of a pipe, you doubled the flow. We now know that friction plays a huge role. A larger pipe is actually more efficient and carries more than double the flow of a pipe half its size. This lack of theoretical physics meant the aqueducts often delivered more water than the books said they should, leading to overflow, or less, leading to shortages. Let us look at a specific structural application of this water that goes beyond drinking and bathing: the industrial mill. The Barbegal complex in southern France is the supreme example. Here the aqueduct was not just a supply line, it was a machine. The structural spec at Barbegal involved splitting the aqueduct flow into 2 parallel channels as it reached a steep hill. These 2 channels then cascaded down the slope, feeding a series of 16 water wheels arranged in 2 parallel rows of 8. This was a factory. The water would hit the top wheel, turn it, fall into a basin, flow out to hit the second wheel, and so on, all the way down the hill. The gradient here was steep, about 30 degrees. The structural engineering required to anchor these mills into the hillside was immense. They cut chambers into the rock for the wheel pits. The water channels were lined with wood and stone. The power generated by this cascade was used to grind flour. It is estimated that the Barbegal mills could produce 4.5 tons of flour per day, enough to feed the population of the nearby city of Arelate, Arles. This demonstrates a kinetic spec of the aqueduct. The potential energy of the water, gained by keeping it high in the mountains, was converted into mechanical work. We see similar, though smaller, setups on the Janiculum Hill in Rome, where the water of the Aqua Traiana drove mills that ground the grain for the city's bread dole. The aqueduct was the power grid of antiquity. Returning to the domestic sphere, let's examine the plumbing logistics of the private home. If you were a wealthy Roman, you didn't just ask for water, you hired a plumbarius. The lead pipes used in your home were not the property of the state. They were your property. You paid for the lead. You paid for the installation. The pipes, or fistulae, were often laid in the walls or under the floors. But unlike modern pipes, they were rarely embedded inside the concrete. They were placed in channels or chases cut into the masonry, covered with a tile or a flat stone. This was a maintenance access spec. If a pipe burst, you didn't want to destroy your mosaic floor to fix it. You wanted to lift a cover stone. The joinery of these pipes helps us understand the pressure rating of the system. The soldered seams were strong, but the lead itself was soft. Under high pressure, lead pipes tend to creep or expand, eventually thinning and bursting. This material limitation dictated the maximum height of the distribution towers. They could not pressurize the system too much, or the domestic pipes would fail. Thus, the aqueduct system was a low-pressure, high-volume network. We must also consider the thermal spec of the aqueducts in relation to the Great Baths, Thermae. The baths of Caracalla or Diocletian were not just pools, they were heat exchangers. The aqueduct supplied the water, but the hypocaust supplied the heat. The water had to be routed to massive copper boilers located directly over the furnaces. The logistics of the flow were critical here. Cold water entered the system. It was preheated in a tepidarium tank, then fully heated in the caldarium boiler. The structural integration of the water pipes with the hot air flues of the furnaces required precise masonry. The pipes had to be supported so they wouldn't sag when hot. They had to be accessible for the constant removal of limescale, which precipitates much faster in hot water. A boiler scaled up with sinter would explode or melt. Therefore, the boiler room of a Roman bath was a place of constant maintenance activity, hidden from the eyes of the bathers. The brick industry that supported these structures deserves a closer look. In the mid-imperial period, the structural spec for walls shifted almost entirely to brick-faced concrete, opus testaceum. The bricks used were not the small rectangular blocks we use today. They were large, flat tiles. The standard sizes were bessels, roughly 20 centimeters square, sesquipedales, roughly 44 centimeters square, 1.5 Roman feet, bipedales, roughly 60 centimeters square, 2 Roman feet. For the facing of an aqueduct pier, these large tiles were typically cut into triangles. The pointed end of the triangle was inserted into the concrete core, while the long, flat edge formed the visible surface. This triangular shape acted as a tooth, bonding the facing inextricably to the core. When you look at a ruined aqueduct arch today, you might see rows of large, flat bricks running horizontally through the structure at regular intervals, breaking up the smaller brick facing. These are bonding courses of full bipedals. Their structural purpose was to level the work and to distribute the weight evenly across the entire thickness of the wall during construction. They prevented the wet concrete from bulging out the facing. They act as horizontal reinforcement layers, a primitive form of lamination. In the later empire, as resources became scarcer, we see a shift to opus mixtum, a mixture of brick bands and reticulatum, small stone blocks, and later still, opus vitatum, which used alternating courses of small rectangular stone blocks and bricks. By analyzing the masonry spec, the ratio of brick to stone, the thickness of the mortar joints, archaeologists can date a repair to within a few decades. Let's discuss the failure modes of an aqueduct. What happens when the structural specs are violated? We have historical records of collapses. The Aqua Claudia, despite its grandeur, was plagued by problems. Tacitus tells us that it was interrupted by frequent failure. The problem was likely the foundation. The heavy structure, built on the soft volcanic soil of the Campagna, settled unevenly. When an arch settles, the delicate waterproof lining of the channel cracks. The water leaks out. The water saturates the soil around the pier, softening it further. The pier sinks more. The arch deforms. Eventually the keystones slip and the structure collapses. To combat this, Later engineers added buttressing specs. If you look at the Aqua Claudia today, you will see that the original clean lines of the stone piers are often encased in bulky, ugly brick sheaths. These are reinforcing clamps added by Titus or Septimius Severus. They wrapped the cracking stone in a corset of new concrete and brick to hold it together. It wasn't pretty, but it kept the water flowing. Another failure mode was the seismic spec. Rome is in a seismically active region. A long, rigid stone line is very vulnerable to earthquakes. The dry stone arches, like at Segovia or the internal structure of the Roman ones, actually handled this better than the solid concrete ones, as the stones could shift slightly without breaking. But the waterproof lining was always the casualty. After an earthquake, the tectors, plasterers, would have to crawl the entire length of the line, tapping the walls to find hollow spots where the lining had detached and patching the cracks. Let us detail the aesthetic spec of the water features themselves. The Romans did not just want water, they wanted the look of water. In the Nymphaeum, a monumental fountain, the water was made to cascade over steps, or water stairs. The spec for these stairs involved cutting the stone lips at a specific angle to create a smooth, glassy sheet of water, or a roughened edge to create a sparkling, white water effect. They used colored marbles, green cipollino to mimic the depths of a river, or white Carrara to frame the clarity of the stream. The interaction of light and water was a design parameter. In the grottos and dining areas of villas, the aqueduct water flowed through channels lined with blue glass mosaic, creating an artificial stream that glittered in the candlelight. But let's return to the boring, essential darkness of the underground channel. The air management spec. We touched on vents, but consider the aerodynamics of the water surface. As water rushes down a channel, it drags air with it. In a siphon, this entrained air can accumulate at the high points, knees, of the pipe run. If an air pocket forms, it restricts the flow, just like a solid blockage. To prevent this, the Romans sometimes installed colliviaria, vents on the siphon bridges. These were small towers that allowed the trapped air to escape while keeping the water in. The valve mechanism for this is not fully understood, but it likely involved a float that would rise with the water to seal the vent and drop when air accumulated to let it out. This implies a dynamic, moving part within the stone infrastructure. The security spec of the aqueducts became more critical in the late Empire. As the barbarian threat grew, the aqueducts became liabilities. The Goths, under Vitiges in 537 AD, cut the aqueducts to thirst out Belisarius and the Romans. But they also tried to use the aqueducts as invasion routes. The large channel of the Aqua Virgo, or the Claudia, was big enough for a file of soldiers to walk through. Belisarius had to brick up the intakes and the outlets to prevent the Goths from crawling into the city through the water pipes. The structural asset became a tactical vulnerability. The man-sized channel, once a spec for maintenance, became a spec for infiltration. Let's focus on the lime-burning industry that grew out of the aqueducts. The sinter, calcium carbonate, removed from the channels was chemically identical to limestone. Rather than quarrying new stone, the Romans often built lime kilns right next to the aqueduct maintenance shafts. They would harvest the waste product of the water, burn it, and turn it into quicklime, which was then used to make mortar to repair the aqueduct. This is a perfect closed-loop maintenance cycle. The aqueduct grew its own repair material. We should also mention the surveying markers that remain. In the tunneled sections, we sometimes find oil lamp niches cut into the walls at regular intervals. These were not just for light, they were for sighting. A surveyor could align a series of lamps to check the straightness of the tunnel. We also find numerical markings painted or carved on the walls, indicating distance or section numbers, likely used for payment of the contractors who dug the tunnels. Section 15. Completed. The contract spec for building an aqueduct was likely detailed in terms of volume of rock removed and volume of masonry installed. The labor was immense. It is estimated that the construction of the Anio Novus and Claudia took 14 years. 14 years of constant digging, hauling, and stacking. The slow pace of construction meant that the design often evolved while it was being built. We see changes in the style of brickwork, from one end of an aqueduct to the other, marking the passing of time and the changing of contractors. As we move from the moving line of the aqueduct to the stationary reserve, we encounter a new set of structural specifications, the specs of the great cisterns. While the Castellum Aquae was a distribution box, a switching station, the cistern was a battery. It stored potential energy and essential volume against the possibility of a cut in the supply or a siege. The most spectacular example of this structural typology is the Piscina Mirabilis in Misenum, on the Bay of Naples. This was not a civic reservoir for a town. It was the strategic water supply for the Classis Misenensis, the imperial naval fleet. The structural requirement here was massive capacity and absolute impermeability. The Piscina Mirabilis is a subterranean cathedral. It is excavated into the soft, tough rock of the hillside. It measures roughly 70 meters long by 25 meters wide and 15 meters deep, but it is not a simple box. To support the earth above, the engineers left 48 cruciform, cross-shaped pillars of rock standing in 4 rows of 12. The structural spec for these pillars is precise. They support a barrel-vaulted ceiling. The entire interior, walls, floor, pillars, and ceiling, is lined with a thick coat of opus cyanum. But here, the application of the waterproof mortar reaches its highest level of craft. The walls were often treated with a final wash of pure lime and oil, or even wax, to create a surface so smooth that algae could not find a foothold. Consider the cleaning spec for such a vast tank. The floor of the Piscina Mirabilis is not flat. It has a gentle slope towards one end, where a limaria, a depression or sump, collected the sediment. But there is another detail, the pumping sump. In the center of the nave, there is a depression located directly under a shaft in the roof. This was for the hostrum, a bucket and pulley system, or a mechanical water lifting device, used to draw water up to the surface when the gravity feed was turned off. The maintenance of these cisterns required a specific architectural feature: the stairs. 2 grand staircases descend into the Piscina Mirabilis, one in the northwest corner and one in the southeast. These were not for the water. They were for the workers. Imagine the echo in that vast, empty chamber when the water was drained for cleaning. The sound of 40 men scrubbing the walls would reverberate through the pillars like a chant. Now, let us transport the structural specs from the warm Mediterranean to the cold north. The Eiffel Aqueduct supplying Cologne, Colonia Claudia Ara Agrippinensium. Here, the enemy was not heat or evaporation, it was frost. The structural specifications for the Eiffel Aqueduct had to account for the expansion of freezing water. If the water in a channel freezes, it expands by about 9%. In a closed stone channel, this force is enough to shatter the masonry. Therefore, the Eiffel line was buried significantly deeper than its Italian counterparts, typically 1 meter or more below the surface, to stay below the frost line. The material spec also changed. In Italy, they used pozzolana and limestone. In the Rhineland, there is no pozzolana. Instead, the Roman engineers discovered a local substitute, trass. This is a volcanic tuff found in the Eifel Mountains. When ground into powder and mixed with lime, trass exhibits the same hydraulic properties as pozzolana. It sets underwater. This demonstrates the adaptability of the Roman engineering code. The chemistry remained the same, but the ingredients were sourced locally. The channel of the Eifel Aqueduct was also wider than usual, about 70 centimeters, but the water level was kept lower. This air gap above the water acted as insulation. The concrete walls were poured against wooden shuttering. The grain of the wood, often still visible in the concrete today, a fossilized record of the carpentry used in the 1st century AD. Let us return to the pipes and address a common structural query, the lead question. Did the fistulae poison the Romans? The structural reality of the aqueduct argues against widespread lead poisoning, Saturnism, from the water supply itself. There are 2 reasons for this, both based on physical specs. First, the water in Rome was hard. It was rich in calcium carbonate. As we have noted, this mineral precipitates out of the water constantly. Within a few months of installation, the inside of a lead pipe would be coated with a thin layer of sinter. This crust effectively sealed the lead away from the water. The water was flowing through a tube of rock, not a tube of metal. Second, the flow was continuous. Lead dissolves into water most effectively when the water is stagnant and acidic. Roman aqueduct water was moving fast and was generally alkaline. There was no time for the chemical reaction to occur in significant amounts. The structural spec of constant flow was a health safety feature, albeit an accidental one. However, there was an alternative to lead, the terracotta pipe, tubuli. In some provincial aqueducts and for local agricultural distribution, fired clay pipes were used. These had their own structural geometry. One end of the pipe was narrowed, the spigot, to fit into the flared end, the socket, of the next pipe. The joint was sealed with lime mortar or a mixture of quicklime and oil. The structural advantage of terracotta was that it was cheap, easy to produce locally, and added no metallic taste to the water. The disadvantage was its low tensile strength. It could not withstand high pressure. If you tried to use terracotta for a deep siphon, it would burst. So, the material spec was dictated by the topography. Lead for the valleys, high pressure. Terracotta or masonry for the gentle slopes, low pressure. In Turkey, specifically for the city of Constantinople, later Istanbul, the structural ambition rivaled and eventually exceeded Rome. The aqueduct of Valens, completed in the late 4th century AD, is a testament to the late Roman commitment to these specs. The Valens Aqueduct Bridge spans the valley between the hills of Constantinople. It is a double-tiered arcade. But the structural difference here is the use of ashlar masonry. The blocks are large, well cut, and the core is filled with mortar and rubble. The scale is massive because the water had to be brought from the Thracian forests, over 120 kilometers away. Later, this system was expanded to over 250 kilometers, the longest of all ancient aqueduct systems. The bridge spec in the east often utilized pointed arches in later repairs, a precursor to Gothic architecture. But the original Roman sections relied on the standard semicircular arch. The stone used was often a local limestone that weathered to a honey gold color. The interaction of these stones with the seismic activity of the region was a constant battle. The piers were often reinforced with buttresses that widened the footprint of the structure, making it squat and solid against the shaking earth. Let's zoom in on the tools of the mason that built these structures. The accuracy of the aqueduct relied on the libella. This was an A-frame level. It looked like the letter A. A plumb line hung from the apex. When the string lined up with a mark on the crossbar, the surface under the legs was level. But for lifting the massive stone blocks of the arcades, they used the Lewis bolt, or Lewison. This is a brilliant piece of structural hardware. To lift a heavy block without wrapping ropes around it, which would get in the way of setting it next to another block, the masons cut a dovetailed hole in the top of the stone. They inserted 3 metal pieces into this hole, 2 wedge-shaped outer pieces, and a straight central locking piece. When the crane pulled up on the ring attached to these pieces, the wedges were forced outward, gripping the stone from the inside. The heavier the stone, the tighter the grip. Once the stone was set in place, the central pin was knocked out, the wedges collapsed, and the tool was removed, leaving only a small hole in the top of the block, which would then be covered by the mortar of the next course. The cranes themselves, the polyspastos, were treadwheel cranes. 2 or 4 men would walk inside a large wooden wheel, turning the axle. The mechanical advantage provided by the system of pulleys allowed a few men to lift tons of rock. The hoisting spec dictated the size of the stone blocks. The blocks could not be heavier than the crane's capacity, so the architecture was limited by the machinery. We must also consider the hydraulic mortar additives. To make the opus signum even more waterproof, the Romans didn't just use pottery shards. Vitruvius mentions the use of pork fat, curdled milk, and even blood in the mixture. These organic additives acted as plasticizers and water repellents. The biological spec of the mortar is a fascinating study in ancient chemistry. They were essentially creating a polymer-modified cement using what they had in the kitchen. There is a specific type of aqueduct structure we haven't detailed yet, the cascade. In steep terrain, where the gradient was too steep for a smooth channel, which would cause erosion, the engineers built a series of steps. The water would fall from one small basin to the next, dissipating its energy at each step. This energy dissipation spec is crucial. We see this in the aqueduct of Side in Turkey and in sections of the Aqua Marcia. The noise of these cascades would have been significant. A roaring staircase of water hidden in the forest. The stone steps would wear down over time, requiring replacement. Let us look at the cross-section of a typical trench construction again. When digging the trench for the underground channel, the shoring spec was vital. In loose soil, as the slaves dug down, they had to hold back the earth with timber planks and struts. If this timber was green, unseasoned, it might warp. If it was too dry, it might crack. The logistics of supplying timber to the aqueduct line were almost as complex as supplying the stone. Once the trench was dug and the channel built, the backfill spec came into play. You couldn't just dump the dirt back in. It had to be packed down in layers to prevent settling later. If the backfill settled, the ground above would sink, creating a depression that collected rainwater, which could then seep down and contaminate the aqueduct. The earth over the aqueduct had to be crowned or mounded to shed water. Now consider the aqueduct of Segovia in Spain again. The defining structural characteristic here is the lack of mortar in the arch joints. This is opus quadratum, squared work. The stability of the structure relies entirely on the precise cutting of the granite blocks and the geometry of the arch. The specs for the piers in Segovia are interesting. They are not solid rectangles. They are stepped. As the pier rises, it gets thinner. This reduces the weight and the material used, but it also lowers the center of gravity. The blocks have small holes visible on their faces. These are the lifting boss holes, or the Lewis bolt holes we mentioned, left visible as a testament to the construction process. The Segovia aqueduct also features a sand trap, or deserenador, before the water reaches the bridge. This is a simplified version of the Piscina Limaria. The channel widens and deepens, slowing the water to drop the granite sand that washes down from the mountains. Without this, the sand would sandblast the stone channel of the bridge, wearing it away in a few decades. In contrast to the stone bridges, we have the wooden aqueduct. Though few survive, we know they existed. In temporary military camps, or as stopgap measures while a stone bridge was being repaired, the Romans built wooden trestles carrying wooden troughs lined with lead or pitch. The timber spec was temporary but essential. The structural lifespan of a wooden aqueduct was perhaps 20 years compared to the 500-plus years of a stone one. Let us contemplate the sound of the aqueduct. A properly functioning aqueduct is not silent, but it is quiet. It is a steady, low-frequency hum. If an aqueduct is making a lot of noise, splashing, gurgling, it means there is turbulence, which means there is a problem with the gradient or an obstruction. The Roman engineers listened to the channel. A silent flow was a smooth flow. The acoustic spec was a diagnostic tool. The inspection regime involved the circuitories walking the route. But how did they check the inside of a siphon? They couldn't. The lead pipes were sealed. If a siphon lost pressure, it was a nightmare. They would have to listen for the hiss of a leak along the ground, or they would look for wet spots. Digging up a siphon to find a leak was a massive operation. They would have to melt the solder, remove the section, replace it, and resolder it, all while the city waited for water. Finally, for this part, let's look at the aesthetic integration of the aqueduct in the villa. For the Emperor Hadrian at his villa in Tivoli, the aqueduct was an architectural toy. He diverted the water to create the canopus, a long canal reflecting statues. The structural spec here was purely visual. The water was used to create a mirror. The edges of the canal were lined with white marble to brighten the reflection. The depth was calculated to prevent weed growth but allow for easy cleaning. Here, the brute force of the aqueduct was tamed into a delicate ribbon of light. The drainage of the valleys. When an aqueduct crossed a valley on a solid wall, a continuous substructure, it acted as a dam. It blocked the natural drainage of the rainwater flowing down the valley. To prevent the aqueduct from being washed away by a flash flood building up behind it, the engineers installed culverts, or arched openings at the base of the wall. These allowed the valley streams to flow under the aqueduct. The sizing of these culverts was a critical hydraulic spec. Make them too small, and the water backs up and topples the wall. Make them too big, and you waste stone arching over empty space. They had to guess the 100-year flood level without modern data. This concern for the 100-year flood brings us to the legal framework that protected these calculated risks. The structural integrity of the aqueduct was not just preserved by stone and mortar, but by the rigid application of Roman law. The Lex Quinctia, passed in 9 BC, is the ultimate legal specification for the water supply. It details the punishments for those who dared to compromise the system. The text of the law is specific and unforgiving. It states that anyone who maliciously damages the conduits, tunnels, or arches must pay a fine of 100,000 sestertii to the Roman people. To put this in perspective, a legionary soldier earned about 900 sestertii a year. The fine was a life sentence of debt. The law also demanded that the perpetrator repair the damage at their own expense. This repair spec ensured that the state did not bear the cost of vandalism. The Lex Quinctia also regulated the right of way. It reiterated the corridor of silence, the 15 feet on either side, but it went further into the agricultural minutiae. It forbade the planting of trees, yes, but also the grazing of cattle. The hooves of heavy animals could compact the soil over a buried channel, or worse, erode the earth covering it. The law treated the ground above the aqueduct as part of the structure itself. Let us examine the specific structural anomaly of the Aqueduct of the Miracles, Aqueducto de los Milagros, in Mérida, Spain. The aesthetic specification here is radically different from the monochrome stone of Segovia or the Gard. The engineers in Mérida used a polychrome spec. The piers are constructed with alternating courses of gray granite blocks and red brick. Typically, it is 5 layers of granite, followed by 5 layers of brick. This was not just for beauty. This was a dampening spec. The brick layers acted as shock absorbers. In the event of an earthquake or settling, the brick, being softer and more flexible than the granite, would absorb the energy and prevent the granite blocks from cracking. It is a composite material strategy, layering hard and soft to create a resilient whole. The visual effect, striped like a rug, is a byproduct of this structural necessity. In Turkey, at the site of Aspendos, we find a completely different solution to the valley crossing problem. Instead of a massive bridge or a standard siphon, the engineers built hydraulic pressure towers. The water arrived at the edge of the valley and flowed into a header tank. From there, it went into a siphon pipe that descended to the valley floor. But instead of crossing a low bridge, the pipe went up a tall masonry tower, then down again, then up another tower, and finally up the other side of the valley. The purpose of these towers is a subject of debate among hydraulic historians, but the prevailing structural theory is that they served as surge tanks. They allowed air bubbles to escape at the high points, preventing airlocks. They also dampened the pressure surges. If the valve at the city end was closed suddenly, the water could rise up inside the open towers rather than bursting the pipes. This is the ancient equivalent of the surge arresters used in modern hydroelectric plants. The Aspendos spec shows a sophisticated understanding of water hammer dynamics. Back in Rome, let's look closer at the chemistry of the flow. The mixing of waters was generally forbidden, but sometimes structural reality forced it. The Anio Novus, with its high volume but muddy water, would sometimes be mixed with the pristine Claudia to increase the volume of the latter. This dilution spec was a controversial management decision. Frontinus complains about it. He notes that the crude Anio water spoiled the clarity of the Claudia. To manage this, a switching station was built near the Porta Maggiore. This complex junction box allowed the equerri to route the Anio Novus into the Claudia channel, or keep them separate, or even route them into the lower aqueducts like the Tupula or Giulia if needed. It was a hydraulic mixing board. The design of the inspection steps inside the channels is another minute detail. In the larger channels, steps were carved into the side of the channel wall near the inspection shafts. These were often just small recessed pockets, barely big enough for a toe. They allowed the maintenance worker to climb down from the shaft into the flowing water. The ergonomic spec here was minimal. It assumed a high level of agility from the Familia Publica. We must also talk about the distribution tanks, castella, in the streets. These were not hidden. They were often raised on brick podiums. The tank itself was usually lead, encased in masonry. The pressure spec inside these local tanks was low. The water simply fell into them from the main pipe and then flowed out to the fountains by gravity. But how did they shut off the water for a specific house? The stopcock, epistomium. These bronze valves were precision engineered. They consisted of a tapered plug with a hole in it, fitting into a tapered socket. To turn the water on, you rotated the plug so the hole aligned with the pipe. To turn it off, you rotated it 90 degrees. The manufacturing spec for these valves required grinding the plug and socket together with abrasive powder, emery, to create a watertight seal. If the fit wasn't perfect, the valve would drip. Archaeological finds show thousands of these valves, ranging from tiny ones for a single house to massive ones for the mains. The handles were often shaped like keys, removable so that unauthorized people couldn't turn the water on. This is the lockout spec of the Roman water grid. Let's descend into the sewers again, the inevitable destination of all this engineering. The Cloaca Maxima was not just a ditch, it was a vaulted tunnel, large enough to row a boat through, as Agrippa famously did during an inspection. The floor of the sewer was paved with basalt blocks, the same stone used for roads, to resist the abrasion of the grit and debris washing through. The connection spec between the street and the sewer was the storm drain. These were large stone openings, often without grates. This posed a safety hazard. People could fall in. But it was necessary for swallowing the torrents of water during a Roman thunderstorm. The aqueduct overflow flushed these sewers constantly. Without the aqueducts, the sewers would have been stagnant cesspits. The sanitation spec was a flow-through system. We should also mention the fulling industry again. The Follonica laundries were the recycling plants of the aqueduct system. They were often located near the major distribution points to catch the overflow. The structural setup of a Follonica involved a series of treading tanks, saltus. The workers would stand in these tanks, stomping on clothes in a mixture of water, urine, and fuller's earth, clay. The urine provided the ammonia for cleaning. This implies a urine collection spec for the city. Large jars, dolia, were placed on street corners for men to urinate in. This liquid was then harvested by the fullers. The Emperor Vespasian even taxed this trade, leading to the famous phrase, pecunia non olet. Money does not smell. The aqueduct water was the final rinse in this process, washing away the ammonia and the dirt. Let's look at the Pont du Gard's specific width spec. The three tiers are not the same width. The bottom tier, carrying the road and the weight of the structure, is 6 meters wide. The middle tier is 4 meters wide. The top tier, carrying the channel, is only 3 meters wide. This tapering is a stability spec. It keeps the center of gravity low and reduces the amount of stone required. The arches of the top tier are identical in size, creating a rhythm, while the arches of the lower tiers vary in width to match the terrain and the river flow. The largest arch spans the river itself, a structural leap of 24.5 meters. To build the arches of the Pont du Gard, the Romans used centering, wooden frameworks that supported the stones until the keystone was placed. The scaffolding spec is visible in the stone itself. On the face of the masonry, we see projecting blocks that were not cut flush. These were supports for the wooden scaffold. They were left in place to facilitate future repairs. It was a maintenance-ready design. In the Aqueduct of Cologne, the inspection spec included a footpath alongside the channel in the underground sections. This is rare. Usually, you had to walk in the water, but the Eiffel Aqueduct was wide enough for a dry path. This suggests a higher frequency of inspection, or perhaps a desire to keep the inspectors dry in the cold German climate. The settling tanks, piscina, had a hydraulic geometry. The floor was often sloped steeply towards the central drain. This utilized gravity to help the sludge slide out when the sluice was opened. Some tanks had a bypass channel built around them. This allowed the water to continue flowing to the city while the tank was being cleaned. The redundancy spec ensured continuous service. Let's consider the tools of the digging. The delabra was the Roman pickaxe. One side was a pick for breaking rock, The other was a mattock for cutting through roots and moving soil. The iron head was mounted on a wooden handle. Millions of cubic meters of earth were moved by this simple tool. For the rock tunnels, they used the fire-setting spec. They would build a fire against the rock face to heat it, then splash cold water. Often vinegar was rumored to be used, though water is sufficient, on the hot rock. The thermal shock would crack the stone, making it easier to pick away. This technique consumed vast amounts of wood and oxygen, making the air in the tunnel even more unbreathable. The ventilation shafts, lumina, were not just vertical holes. They were often stepped or slanted to prevent rain and debris from falling directly into the channel. In deep tunnels, they were sometimes dug in pairs to create a convection current, cool air going down one, hot air coming up the other. Now, the material logistics of the brick production. The bricks for the aqueducts were produced in massive rural yards. They were dried in the sun for weeks before firing. A drying spec was crucial. If a brick was fired while still damp, the steam inside would blow it apart. The drying sheds were long, open-sided structures. Once fired, the bricks were transported by river barge, on the Tiber or Anio, to the city. The transport spec relied on water to build the water system. The heavy materials, stone, brick, lead, were floated down from the hinterland. The aqueducts were essentially built out of the landscape they traversed. Let's talk about the measurement of the water again. The calyx, nozzle. We mentioned it was bronze, but the calibration spec was even more detailed. The length of the bronze nozzle was specified as not less than 12 digits, roughly 22 centimeters. This length ensured that the flow was laminar, smooth, as it entered the private pipe, making the measurement accurate. A short nozzle would allow turbulent, faster flow, cheating the system. The fraud detection team. Frontinus describes discovering secret taps. These were unauthorized pipes inserted into the conduit by farmers passing by. They would bore a hole in the stone channel and insert a reed or a small lead pipe to water their fields. This parasitic speck was a constant drain on the system. The circuitors had to physically walk the top of the buried channel, looking for wet spots or suspicious lush vegetation that indicated a leak or a theft. The end of the aqueducts was a destructuring process. In the 6th century, during the Gothic Wars, the Goths cut the aqueducts. But the destruction wasn't just military. It was a failure of the maintenance spec. Without the imperial administration to pay the familia, the sinter was not chipped out. The channels narrowed. The leaks were not patched. Roots broke the masonry. The water stopped flowing to the hills. The baths went dry. The population of Rome moved down from the hills to the Campus Martius, the low field by the Tiber, where they could draw water from the river and from wells. The urban speck of Rome collapsed from a high-pressure hilltop metropolis to a low-lying riverside village. The aqueducts remained as giants' bones, their function forgotten by many, stripped of their lead and stone for lesser buildings. But before the fall, the system was a machine of precision. The water clocks, clepsydra, of Rome were calibrated by this flow. While simple water clocks dripped from a bowl, the more complex ones relied on a constant, regulated flow from the aqueduct line to measure time. The temporal spec of the city was tied to its hydraulic spec. Consider the thermal shock on the masonry. In the summer, the stone bridge is baked by the sun, reaching perhaps 50 degrees Celsius. Inside, the water is a cool 12 degrees. This temperature differential creates immense stress in the stone. The expansion spec of the materials had to be compatible. The Roman concrete, with its large aggregate, was remarkably stable thermally. resisting the cracking that would destroy a modern, rigid structure. The aqueduct at Metz in France. This is a unique case where the bridge crossed the Moselle River. It was a double bridge. The water channel was paired with a road bridge. This dual-use spec is efficient. Why build two sets of piers when one will do? The travelers could hear the water rushing beside them as they crossed the river. In Caesarea Maritima, Israel, the high-level aqueduct brought water from the Shuni Springs. But as the city grew, they needed more. They built a second channel right up against the first one. They didn't build a new bridge, they just widened the existing one. This expansion spec is visible today. You can see the seam where the new arch leans against the old arch. It is a visual history of urban growth. The Zagouan aqueduct to Carthage had a massive collection complex at the source, the Temple of Water. This was a semicircular colonnade built right against the mountain where the spring emerged. The religious spec was intertwined with the engineering. The source was sacred. Neptune and the nymphs were worshipped there. To pollute the source was not just a crime, it was a sacrilege. This spiritual protection was a layer of the security system. Let's look at the drop shafts. In some steep terrains, rather than a cascade, the Romans used a vertical shaft to drop the water level. The water would pour down a shaft, hitting a stone bottom, and then flow out horizontally. This created a lot of turbulence and air entrainment. To manage this, the receiving chamber at the bottom had to be large and vaulted to contain the splash. This is an energy dissipation chamber. The lead poisoning question again. One detail often missed is the tap water versus aqueduct water. The water in the main aqueduct channel never touched lead. It touched opus signinum. Only the final distribution network was lead. And since the water flowed constantly, the residence time in the lead pipe was short. The people most at risk were the plumbari, who worked with the molten metal, and perhaps the heavy drinkers of wine, which was sometimes sweetened with lead acetate, sugar of lead, not the drinkers of water. The mortar analysis of the aqueducts reveals the sourcing spec. We can tell where the sand came from. In Rome, they used distinct types of volcanic sand, pozzolane Ross and pozzolane Nere. The Ross, red, was stronger and used for the structural arches. The Nere, black, was used for wall infill. They knew the strength spec of their color-coded sands. Let us transport ourselves to the city of Nemausus, modern-day Nimes in France, to examine one of the finest surviving examples of a distribution hub structural spec, the Castellum Divisorium. Unlike the hidden subterranean junction boxes of Rome, this structure remains visible, offering a clear diagram of Roman hydraulic logic. The Castellum at Nîmes sits at the end of the long aqueduct line that includes the Pont du Gard. The water enters a circular basin, roughly 5.5 meters in diameter and 1 meter deep. The basin is carved from rock and lined with cut stone blocks. The arrival of the water is not a violent crash. It enters through a rectangular sluice designed to smooth the flow into a placid pool. The distribution spec here is radial. Looking at the basin, we see 10 circular holes punched through the stone parapet wall. These are the sockets for the large lead mains that fed the different quarters of the city. Originally, these holes were fitted with bronze collars and lead pipes. The floor of the basin features a cleaning spec we have discussed before, but here it is beautifully executed, a gentle slope towards a central drain. This drain was controlled by a movable barrier. When the sediment built up, sand, leaves, the occasional snail shell, the Aquarius would close the 10 city pipes and open the central purge valve. The rush of the incoming water would sweep the floor clean, flushing the debris into the city's sewer network. We also find evidence of a railing. Holes in the top of the stone wall suggest that a metal grill prevented people from falling into the drinking supply. This is a safety spec integrated directly into the masonry. Moving north to Lugdunum, we encounter the Gear Aqueduct. This line is famous for its aggressive use of the inverted siphon. While most aqueducts avoided high pressure, the Gear embraced it. It features not one, but 4 massive siphons. The structural spec of the Gear siphons required the construction of specific ramp bridges. Unlike a normal bridge that supports a flat channel, a siphon bridge must support sloping pipes. The bridge itself had to follow the curve of the pipe, down the valley side, across the bottom, and up the other side. The siphon of Bonan, part of the Gear line, is a prime example. The header tank and the receiving tank are still visible ruins. The drop is 123 meters. The pressure at the bottom was roughly 12 atmospheres. This is immense. To contain this pressure, the Gear used 9 parallel lead pipes, each roughly 27 centimeters in diameter. The lead was embedded in the masonry of the ramp to prevent it from bulging. The anchoring spec was vital. A lead pipe under pressure wants to straighten out, like a garden hose when you turn on the tap. This force would rip the pipe apart at the bends. Therefore, at the bottom of the valley and at the top of the slopes, the pipes were encased in heavy blocks of stone or concrete to physically hold them down. Let us consider the stratigraphy of the sinter. To a Roman maintenance worker, the calcium carbonate deposit was just waste. To a modern archaeologist, it is a hard drive of data. The layers of sinter in an aqueduct channel are like tree rings. A thick, porous layer might indicate a period of high flow and turbulence. A thin, dense layer might indicate a period of low flow. A layer of dirt or charcoal trapped between the calcite layers indicates a specific event, a storm that washed soil into the source, or a forest fire nearby. By analyzing the isotopes of oxygen and carbon in these stone layers, scientists can reconstruct the temperature of the water and the climate of the region, season by season, year by year. We can literally read the droughts of the 2nd century AD in the stone crust lining the Aqua Marcia. The data storage spec of the aqueduct was unintentional, but permanent. The military camp construction phase. When a legion built an aqueduct, the logistics were militarized. The soldiers themselves often provided the labor for the difficult trenching, while specialists did the masonry. The camp spec for the workers involved temporary barracks, field kitchens, and latrines moved along the route as the construction progressed. We have found inscriptions in North Africa where a legionary detachment records the completion of a specific tunnel section. Legio III Augusta built much of the water infrastructure in Numidia. The discipline required to march in formation was translated into the discipline required to dig a perfectly straight ditch for 20 miles. The centurion became the foreman. Let's look at the drop shaft hydraulics. In the Gear Aqueduct and others with steep gradients, the engineers sometimes used a series of vertical wells to lower the water level rapidly without a long, expensive cascade. The water flows to the edge of a shaft, drops 2 or 3 meters vertically, hits the bottom, boils with turbulence, and then flows horizontally to the next shaft. The structural problem here is the impact energy. The water hitting the bottom of the shaft acts like a hammer. If the floor is just stone, it will erode quickly. The impact spec solution was a water cushion. The floor of the shaft was often deepened to create a permanent pool of standing water. The falling water would hit this pool, not the stone. The liquid absorbed the shock of the liquid. The overflow from this pool then continued down the line. It was a self-protecting system. The inspection of the uninspectable. How did they check the bottom of a deep well or a siphon venter? Mirrors. There is evidence that surveyors used polished bronze mirrors to reflect sunlight down into deep shafts to inspect the lining without descending. A primitive fiber optic spec using reflected natural light. The Churchill Aqueduct in Algeria presents a specific bridge stability spec. The bridge over the Oued Bella is 35 meters high, but the ground here is unstable clay. To prevent the piers from sliding, the Romans built a massive foundation raft. They connected the bases of the piers with a continuous platform of concrete and masonry across the valley floor. The piers didn't just sit on the ground, they sat on a unified artificial floor. This distributed the weight and prevented differential settling. Let's touch on the water lifters. While the aqueduct relied on gravity, sometimes the destination was higher than the arrival point. In the baths of Caracalla, for instance, water had to be lifted to header tanks to create pressure for the fountains. The noria was the standard machine for this. A large wooden wheel, driven by the flow of the water itself or by animal power, carried clay pots or wooden boxes on its rim. As the wheel turned, the pots dipped into the reservoir, filled, rose to the top, and emptied into a higher trough. The axle spec of a noria was the weak point. It had to support the weight of the wet wheel. These axles were often made of iron-bound oak, turning in bronze bearings lubricated with animal fat. The squeak of the noria would have been a constant background noise in the service areas of the baths. For higher lifts, they used the cochlea. This was a wooden cylinder with a helical blade inside. It was tilted at an angle. A man would walk on top of it, turning it like a treadmill. The water would be trapped in the pockets of the helix and carried up. The seal spec between the blade and the casing was critical. If the gap was too big, water leaked back down. They used pitch and tar to seal the wood. Let's discuss the opus mixtum aesthetics and structure. In the late Empire, specifically in the 3rd and 4th centuries, the aqueducts were built with alternating bands of brick and tufa block. Visualizing this, 1 meter of white rectangular stones, then a band of 5 red bricks, then another meter of white stones. The structural reason: the brick bands leveled the wall. If the stone layers were getting slightly uneven, the brick layer provided a fresh, flat start. The economic reason: it used up available scrap stone while maintaining the strength of brick. The aesthetic result: a striped bacon look that became fashionable in late antiquity. The safety valve. Did they have pressure relief valves? Not in the modern sense of a spring-loaded valve, but they had overflow weirs. At the castellum, if the pressure rose too high, the water level in the tank would rise. Before it could burst the pipes, it would flow over the top of a stone wall and into the drain. The pressure regulation spec was simply a hole at a specific height. Passive, fail-safe gravity. The aqueduct as a road. We mentioned the Pont de Garde, but many aqueduct bridges served as footbridges for the locals. The maintenance path was often used by farmers. However, this was officially discouraged. Security gates were installed at the ends of bridges to keep unauthorized people off the high wire. The ruse spec. When an aqueduct was damaged beyond repair, or when the city shrank, the structure was cannibalized. The lead pipes were the first to go, melted down for weapons or coffins. The large stone blocks were taken for fortress walls. But sometimes, the aqueduct became a house. In Rome, during the Middle Ages, people built small houses inside the arches of the Aqua Claudia. They used the aqueduct piers as the side walls of their homes and built a roof between them. The structural spec of the aqueduct transitioned from water carrier to human shelter. This parasite architecture preserved many arches, as destroying the arch meant destroying the home. The thermal expansion, in long, straight sections. A masonry channel 10 kilometers long will expand and contract with the seasons. While stone is rigid, the sheer length accumulates movement. The Romans generally did not use expansion joints in the modern sense. Instead, the sinuous nature of the route, curving around hills, allowed the structure to breathe slightly. The curves acted as springs. A perfectly straight aqueduct would be more prone to cracking from thermal stress than a winding one. Let's look at the standardization of the stone. In the quarry, the blocks were often cut to standard dimensions: 2 Roman feet by 2 Roman feet by 4 Roman feet. This modularity allowed the masons to work fast. They didn't have to measure every stone, they just stacked the Lego blocks. The quarry spec dictated the construction speed. The aqueduct of Metz again, the double bridge. The fact that the water channel was open to the air on top of the bridge in such a cold climate is a puzzle. It implies a high flow rate that prevented freezing, or perhaps a wooden cover that has since rotted away. The roof spec is often the hardest to determine archaeologically, because roofs were often made of wood or tiles that were stolen. The settling tank cleaning cycle. How often did they clean them? We suspect it was based on the season. After the spring rains or autumn storms, the water was muddiest. The cleaning gangs would be deployed then. The maintenance calendar was tied to the weather. The mortar analysis, again. The grain size of the sand in the mortar. In the waterproof lining, the crushed pottery was graded. They used larger chunks in the base layer and very fine dust in the top layer. This gradation spec created a density gradient, making the final surface incredibly tight and smooth. The water rights legal disputes. We have records of lawsuits. A city sues a landowner because he diverted the stream that fed the aqueduct, or a dispute between 2 towns sharing a water source. The legal spec was as complex as the engineering. The emperor often had to intervene personally to adjudicate these water wars. The inscription spec. The monumental inscriptions on the arches were not just bragging. They were legal documents carved in stone. They stated the funding source, the repair history, and the emperor's benevolence. They often listed the length of the repair in paces. Restored the channel for 5,000 paces. This was public accountability, the substructure versus arcade. When the ground level was only slightly lower than the channel, they built a solid wall instead of arches. This was cheaper and stronger, but it blocked movement across the land. Arches were only used when they needed to let water or people pass underneath, or when the height made a solid wall uneconomical. The tipping point spec between wall and arch was usually around 2 or 3 meters of height. And so, whether supported by a solid wall or a soaring arch, the water continued its journey. Unyielding, constant, flowing down, always down, towards the sea. The weight of the water, the strength of the stone, the silence of the tunnel, 1 meter at a time, 1 drop at a time. These are the quiet frontier skills that built the world, hidden in the monotonous precision of the gradient. Thank you for traveling back in time with me tonight. I hope the steady flow of history has helped you find your own quiet rhythm. If you are still awake, let the gravity of the water pull you into sleep. Good night. If this journey through the duller side of history helped you unwind and maybe even drift off, please let me know. First, hit that like button if you enjoyed this historical lullaby. Second, Subscribe to the channel so you don't miss future installments of history too boring to keep you awake. Finally, I'd love to hear your thoughts. Drop a comment below about which historical topic you find so mundane. It deserves to be our next sleepy video. Your suggestions will shape our journey into the world's most delightfully dull past.